it's really great to have someone who has worked for quite a long time with a different perspective from those that we've heard so far today. So Rosanna Smart has her PhDs in economics and has been at RAND Corporation for a number of years working on issues of criminal justice, and is one of the authors of a report that is called The Science of Gun Violence that I imagine she'll say something more about, but it really is a fascinating compendium, and in part was one of the reasons why we wanted to have this gathering and focus it very much on the mathematical aspects of what underlies a lot of those issues. So, Rosanna, thank you very much for being here.
I hope I've turned this on correctly. So I'm going to not bring this to a higher level, but bring this to a more aggregate level and be talking primarily about state policy. So we've talked a bit about local interventions, which are incredibly important, but most of what I have looked at has been with respect to state regulations and state policy related to firearms and firearms violence. Most of this talk is going to be drawing from, as Lou said, a report that was not just me, it was a huge group of RAND researchers called The Science of Gun Policy that I think we can link to through the website. I don't think it's there yet. But it was really taking a review of the literature. So I'm going to be coming from a literature review space. Economists maybe won't like that, but I'm the only one here, so that's fine. But so really we just wanted to look at, this is a really contentious space. If we just take a look at the literature and what's out there, what do we know about the effects of various gun policies on outcomes that are of interest in this debate and outcomes that are of interest to different stakeholders? So a reason to think about state policy, in addition to local interventions, is that a lot of this policy action really occurs at the state level, not the federal level. There's action at the local level, certainly, but in terms of laws and statutes, a lot of those are done at the state level. And I think in kind of thinking about mathematical modeling, it might be important to kind of consider the context of state policy when building models and how the effects of whatever you're looking at might vary depending on that kind of state context. There's what I hope to kind of show you through this is there's really a lot of areas where evidence is thin about the effects of these policies and where new research could be helpful. Some of the reasons for why that evidence is thin has to do with data, some of it has to do with methods, and some of it may just have to do with limited attention. So we can talk about that. And then I think one of the things that really came out of this literature review when we were struggling to understand why sometimes effects were found in widely different directions, even though the same data was used, the same policy was being looked at, is there's a lot of kind of methodological challenges that occur in this literature trying to evaluate state gun policy. And so I think it's important both if you're trying to estimate the effects of a state policy to understand these challenges, but also if you're thinking about using any of these estimated effects in the literature as parameters to inform a model, it's probably good to have an idea of how much you should trust those estimates or not. So our research synthesis, our literature review, we considered 13 kind of classes of state gun policies, and these run the gamut of laws that are focused more on determining who can have firearms or the processes around obtaining those firearms. So that would be like minimum age requirements or waiting periods or permitting laws. There's also laws related to kind of keeping track of where guns are. So that could be like firearm dealers' record keeping requirements. There's also laws that focus primarily on the types of weapons that people can have. So we had bans on assault weapons. And then laws regarding kind of where and in what situations people can carry firearms. So things like concealed carry laws, danger ground laws, and gun-free zones. Notably absent from here as the economist are things that directly regulate price. So I can tell you right now, there's not a lot of literature there, and I actually do think a really important area to think about in modeling exercises would be how responsive people are to costs and to prices in particular, and how responsive kind of different types of people who might use guns may respond. We also considered, so we had 13 classes of gun policies, and then we had 8 outcomes. And here we had outcomes specific to gun violence, so gun homicides and violent crime, gun suicides, mass shootings, officer-involved shootings, so where a police officer shot a civilian. But we also wanted to consider kind of a broader range of outcomes than those that are typically talked about in the public health literature. So things like defensive gun use or gun industry, things that are often brought up as a reaction or a reason to not enact certain gun control policies. So we wanted to kind of paint a wide brush. With that in mind, so we did a systematic search strategy and identified 95-ish hundred articles that we reviewed. Of those, we really wanted to focus on studies that were, had some type of causal inference. So we wanted to get closer to the causal effect of the policy. So to be included in the review after this point, we did require that one, they look at one of the policies and one of the outcomes, but also that they had kind of pre-post, so you could ensure that the policy preceded the supposed effects, and that had a comparison group, so you could kind of get away from just national trends or other things that might have been occurring when the policy passed. So you had a state with the policy, you had pre-post, compared to a state or a situation in which that policy was not in place. After that, we ended up with 63 studies that met our inclusion criteria. So it kind of winnowed things down a bit. I will say a lot of those articles had nothing to do with guns at all. It would be, something about, limiting employer access to watching videos online or something, but it would say like the smoking gun, and so it would get caught up. So I read a lot of things. We read a lot of things, not just me. There were a lot of people who had to read a lot of articles that really had nothing to do with it. But just to give you a sense that this distribution of studies is not evenly spread across policies nor across outcomes. So here on the x-axis, I'm just showing the number of studies. And this doesn't add up exactly to 63 because some studies evaluated multiple policies and multiple outcomes. But here in I'm not showing defensive gun use, gun industry, or hunting and sport shooting. Defensive gun use, there was just one study that goes with stand your ground laws. Gun industry, there were, I think, one study that was for assault weapons bans. There was nothing for hunting and recreational gun use. But you can see here that kind of the vast majority of research has really been in this space of evaluating the effects of concealed carry laws or right to carry on violent crime. This is in part because I think an economist published on this in 1997, and then an economist published saying that was wrong, and then an economist published saying that was wrong. And so it's really driven that kind of wide out. But there's also differences. Violent crime has really received a lot of attention. I will say we're doing an update of this review. And just in 2017 and 2018, there are 38 additional studies. The amount of literature being published in this space seems to be growing quite rapidly, which is more work for us, but is really impressive. And a lot of it is getting published. A lot of it does continue to suffer from some of the same challenges that we'll be discussing. In terms of what has been published recently, I'll say there's been a lot of focus on mass shootings. So these kind of yellow bars that are mass shootings have gone out quite a bit more. I think a bit more with suicide. Waiting period laws and stand your ground laws have also started to receive a lot more attention lately. So I'm not going to get into the details of what we found for each of these, but this is just an overview of the table. So we considered for each of these 54 policy outcome pairs the strength of the evidence based on a number of criteria. And so that criteria included the number of studies. So in general, if it's only one study, we didn't really rate that above limited evidence. We arranged so they could go from no studies to inconclusive to limited to moderate to supportive was kind of the strongest evidence. We considered the number of studies, directional consistency. So did studies tend to find effects that were in the same direction, or did they kind of diametrically oppose each other in terms of what they thought the effects of these policies were? We considered the precision of estimates. And then an important thing we also considered was independent data sets. So a lot of studies in this space are really using the same data over and over. And in most literature reviews and meta-analyses, you don't have that problem. You have numerous different trials or interventions, and then you can kind of combine those in a meta-analytic fashion. You can't do that when everyone is looking at the same data just over slightly different time periods, or saying, I'm going to use a linear model and not a log linear. You can't combine them in that way. So we really upweighted the evidence if they were able to use independent data sets to confirm similar information. And then another thing that we rated on was kind of the methodological challenges that I'll get into, or kind of methodological concerns would tend to downgrade the evidence. And so here I will say there were kind of only two of these combinations where we found the evidence as supportive. So it tended to be in the same direction. They used different data sets, and there were a decent number of studies that had precise estimates, and this was in the case of child access prevention laws. So that can be laws requiring safe storage or laws that impose criminal liability if a child accesses a gun, and there's some nuance to that. But here we did find supportive evidence that these were effective in reducing suicides and accidental injury or death, particularly among youths. I will say the concealed carry laws up there is highlighted because even though it has this wide number of studies, we still rated this evidence as limited. And that is largely because you can find whatever effect you want if you look at that literature. You can find that it's significantly positively affects, so significantly increases violent crime, significantly reduces crime, has no effect, sometimes has an effect, sometimes doesn't have an effect. The reason it's such a long literature is people have argued about this for a long time, and people have employed these different methodological specifications, but no one has really paid a lot of attention to whether the statistical models they are using are appropriate for the data that they are looking at. So that actually drove a lot of our understanding of these methodological problems, was that literature has had a lot of back and forth and brought up a lot of these methodological concerns. They just haven't been solved. So in thinking about the methodological challenges facing these studies, I'll start with kind of the general specification that most of the studies in this literature use, which is kind of known as a difference in differences specification. But at its core, what they're doing is imposing kind of some functional form of the outcome or the expected value of the outcome, which is linked in some way. It can be linearly, it can be through a log link, to some functional form of the policy, which is the beta 1 is the effective interest, and that's the function of policy IT, where I categorizes states and T is typically years, though people have done months or quarters. Actually, there's some states that do days that have their own set of challenges. Alpha T here is typically year fixed effects, sometimes a year linear trend. Gamma I represents either state fixed effects or state random effects, and then there's a bevy of control variables, time-varying state-level control variables that could be included in the XIT. And so here, I think some of the challenges I'll touch on today are issues that we found a lot of researchers in this space face with respect to both defining that policy, coding the time course of a policy's effects, which has actually been talked about a few times today in different contexts, simultaneity and reciprocal causation, statistical power, and kind of type 1 error. I also will say, while often in kind of the theoretical models that guide the decision to estimate the effects of these policies, attention is paid to the assumptions that feed into those theoretical models. Not a lot of attention in this literature has been paid to the assumptions that are implicit in the statistical models that they are using. So I think just overall, that's something that is often absent from this literature. So defining the policies. So one, there's some quibbles about when did these laws take effect. Until recently, so RAND now has a database of state gun laws, and Mike Siegel, funded through RWJ, actually has a really good database of state gun laws as well. When a lot of this literature was done, one of those public databases didn't exist, so it was often, I'll just bag on economists, often economists being like, okay, I think this law was passed this time. And then somebody would say that, no, it was actually a different year. So there's kind of quibbles about the timing of when these laws passed. But I think kind of a broader issue that I sometimes have a hard time wrapping my head around and I go back and forth on is how do we group or class policies? There's kind of a spectrum, like every state policy is a unique snowflake. Even if it's nominally the same, even if it's called a concealed carry law, it's going to be implemented and enforced in a different way depending on the state. But you can't really have a dummy variable for every state that has the law and try to estimate the effects. One, because there's really big problems with inference, but two, you can't say anything generalizable. You can say the concealed carry law in California does this, it does this in Texas. That doesn't tell Wyoming anything about its concealed carry law, or a state that didn't have one, what it would do. So there's kind of splitters and lumpers. So there's some people who think that you should estimate the effects of every state policy separately, and then there's lumpers who are like, no, let's put anything that regulates who can have the gun into the same grouping and estimate those effects. And there's decisions that just need to be made along the way, and different researchers make different decisions about this. I don't have the solution, but I think in any modeling exercise, it's almost potentially easier if you're dealing with a fake, a not real policy. But you should think about the mechanisms by which that policy would affect the outcome and maybe how it might map on to these other policies that do exist, or a policy that might be enacted by a state. A different problem that I also don't have a good solution to, again, these are all just choices I think that modelers have to make, is coding the time course of a policy's effects. And you can think about this on a very small scale or on a very large scale over time. Again, this is something that I was happy to hear talked about earlier today, because even if we agree on what the policy is and when it was implemented, we still have to think about, well, how do we want to specify the functional form of this policy? And there's 3 ways that are commonly done in this literature. It's been brought up most heavily in the concealed carry literature, but it's the dummy model where this policy variable is a 0 for when it isn't in effect. It's a 1 when it is in effect, which basically says there is an immediate and permanent effect of this law. It happens once the law turns on, it's on forever. Other people don't think that it's the correct way to do it. So there's the spline model, which is like a slope. So it's basically, we consider this to be a break in our trend. One of the issues in this literature is often that spline model, and maybe this works in some situations, but has been specified as a trend that continues forever, which if you think about it means that eventually everyone is going to be dead or no one's going to be dead. And that might not be what you think. Maybe there is a case, we're talking about contagion, but I think even in that case, you probably want to have an asymptote to that slope. And then there's the hybrid model, which is they assume there's some immediate effect and then some gradual effect that persists over time. And again, I think it's important to think about kind of the mechanism by which these policies are affecting your outcome. To some extent, you might expect in all cases that the effects of these kind of roll out slowly over time, given most policies affect the flow of guns and not the existing stock. But there are different policies where it might be different. I think one thing that's absent in the literature currently is kind of, and we didn't look at, but I've looked at myself for other purposes, are the first order effects. So I think Sherry had mentioned today, if we're thinking about what are the effects of child access prevention laws on suicide, we might want to think first about, well, how do child access prevention laws affect storage behavior? And if we think that's the mechanism by which they're going to affect suicide, knowing that can help us track out the time course of the effect. If we think the laws largely represent a signal that the state has decided that they're going to take, access, safe storage is important, maybe that's going to be an immediate effect. Maybe it's some combination of the two. But I think getting more of a sense of these first order effects on people's attitudes and people's behaviors could help kind of with understanding the time course of the policy's effects. I also do think that it will depend on the policy. Simultaneity and reciprocal causation are an issue with most policy evaluations. We like to call this type of setup a natural experiment, where we've got, this nice exogenous policy that's occurred, but they're not experiments. Even most local interventions are not kind of at their core experiments. There, I think, are a few. And really these quasi-experimental methods, to appropriately identify the causal effect of the policy, they rely on implicit assumptions that basically there's not something else that is occurring at the same time that would drive both the policy and your outcome, so omitted variable bias, and you try to control for those by including a bunch of time-varying covariates. But at the end of the day, you probably haven't gotten all of them, but I think it's important to carefully think about that. And I think the other one that's kind of more puzzling for me to think about how to deal with are the fact that you're kind of implicitly assuming here that the changes in the firearm policy are driving the changes in the outcome, and not that the changes in the outcome are driving the changes in the policy. And there's been particularly some recent work that has looked at how mass shootings affect policy and has found that these incidents in and of themselves can lead to the policy changes. And so in that case, what you're picking up is not necessarily the effect of the policy, but the effect of the outcome on the enactment of the policy. And so here it's just important, again, to kind of trace out the time path and ensure precedence, ensure that the policy change is occurring before the change in the outcome and not vice versa. And again, this is interesting. I really do want to talk about this more in a mathematical modeling context, because I'm curious about how this kind of reciprocal nature gets built into those models. I think it's an interesting, it's a really difficult problem to deal with in a statistical model, but maybe fairly straightforward in a mathematical model. That's where you guys come in. And then kind of more statistical nitty-gritty is the issue of power, which is kind of the probability that you will be able to detect effect given an effect exists. And in here, what we found, and I'll get into this when I get into the kind of next segment of this, is the models that are looked at in this literature really have very little power. So we typically, if you're writing a proposal for NIH and you have to do a power analysis, you typically say something about 80% power is good. And we found that most of these models have 10% or 20% power. And I think that makes sense, that even if these state policies have potentially large effects, like in terms of the magnitude and what they can actually do in terms of social welfare, it may still be just kind of marginal. So even if if a policy was enacted, and say it was enacted nationally, that would be about 1,000 fewer firearm deaths per year, which I think we all agree would be like a pretty good policy. That's about 3%. And so for these models to be able to pick that up, particularly when you have really variable outcomes, it's quite difficult. And so that limits power. And I think this might not be problematic, you would think, because, well, then you just won't find statistically significant effects. But I think combined with publication bias, right, you can end up in a situation where if you're looking at the literature and you see 10 statistically significant effects, and those studies had 10% power, they probably came from 100 different regressions. And if you think about, well, okay, if their significance level was 5%, you're in a situation where you can be like as likely to be detecting the real effect as you are to be detecting like an artificial effect. Which brings us into another problem, which is these studies also tend to have standard errors that are underestimated. And so this is an issue that I think is widely recognized in statistics, and particularly when you're looking at this kind of course of state level outcomes and how they evolve over time, there's serial correlation. These observations within a given state are not independent. The gun violence last year has a strong correlation with the gun violence this year in general. And without adjustments, just kind of classic standard errors are going to be way too small because you're assuming this independence that does not exist. And so you'll end up over rejecting the null or finding too many effects when they're not actually there. And there's some kind of adjustments like clustering standard errors within states that are supposed to account for this. But it's not clear whether those are sufficient in this setup to actually correct your standard errors accordingly. So to try to get at the type 1 error problem and to try to get at the power problem and to really kind of take a step back and say, okay, let's think about like what is the best way to actually model these outcomes, whether we're interested in a policy effect or not. What are the best statistical models that we can think of that will kind of give us adequate power, that will give us correct inference, and that will have a shot at correctly identifying the effects of a policy? And so for this, and this was largely my colleagues, I'm barely involved, but I hung on by a fingernail. So we ran statistical simulations. And so here, just as some motivation, I'm going to show you, this is a sampling of studies that have tried to estimate the effect of shall issue concealed carry laws on murder. They're all using the same data, different time periods, I will say. You can find whatever you want. And so, yeah, so they really run the gamut. And part of that is driven by the fact that they've all made slightly different choices when they set up their models. So they made different choices about whether they did a linear ordinary least squares model, whether they had Poisson regression instead, whether they had the outcome logged as their dependent variable, whether they weighted by state population, whether they had state fixed effects or random effects, how they adjusted their standard errors. There's a big issue in this literature too in terms of overfitting. So those are starred. So economists love to throw in all the covariates because then we can just abstract from omitted variable bias and say we controlled for everything, we're fine. The problem is like that's great if you have a ton of data. It's not so great when you have a state panel over certain years. So there are, I won't call them out, but there are a few papers in this literature where they have literally 2 observations per parameter, which is not good. So that there's this problem of overfitting. So I mean that messes up your inference, that messes up your power. You're unlikely to detect anything real when you're in that situation. These are not that egregious. I've starred them if they have fewer than 10 observations per parameter, but they can get bad. So in terms of the choices we considered in the statistical simulation that we run, we tried to do what was most commonly done in the literature with a little extra, or just kind of cover the basis of what is done in the literature. So we considered the choice of the model in the link function. So ordinary least squares, Poisson, negative binomial. I don't actually think we considered Tobit, general estimating equations, whether we weighted or not by population, state population, the number of covariates, choice of covariates, how we adjusted the standard errors, whether we included a lagged value of the outcome as a predictor in the model, so whether we specified an autoregressive model, random versus fixed effects for states, whether we included state-specific linear trends that again is supposed to pick up some of that time-varying state-specific unobservables, and then how we coded the effect of the policy. And we actually considered a slightly different set than this, but this is what's common in the literature. And so how we did the simulation was we took real data. And so we're going to focus on gun deaths as our outcome. All I can tell you about is gun deaths, because that's all we've done this for. It might look very, very different for mass shootings, and I'm going to defer to Sherry as being the expert on what to tell you about that. But we figured gun deaths is something that when we did a survey of experts who kind of sat on both sides of either gun control or anti-gun control, gun deaths was something everyone agreed was important to look at in terms of policy. We want to reduce gun deaths. And it's one that doesn't suffer from some of the same issues as mass shootings, and that you have a very rare outcome. So most states have at least one gun death per year over our entire period of study. So it makes it a little bit easier when you want to do a logged outcome. So for each law effect that we imposed in the real data, we ran 5,000 trials for each of 18 different statistical model conditions. Then we estimated the effect of the law, and then we compared how the models performed on recovering the effect, where we knew the true effect because we had artificially imposed it in the data. So just as an example, here I've plotted the gun deaths. Each gray line is a state. The thick black line is the national average. So this is gun deaths from 1979 to 2014, which are the years over which we ran the simulation. So for the purposes of the simulation, we would randomly select a subset of states. In this case, I'll say 3 states, and we'll say these 3 states are the ones that passed the law. We would randomly select a law implementation date. We tried to make these kind of align with when gun policies had been passed over the time period that we were looking. And then we would introduce a law effect. So in this case, we've introduced a 3% increase. So we've assumed homogeneous effects across states, which is an assumption within our model. And we've assumed in this scenario that that effect is immediate. So this is just kind of the basic outline of how we took the real data, imposed artificial law effects, and then applied then simulated it multiple times. So we would repeat that 5,000 times. And that would give us a good sense of the number of times we correctly identified there was an effect. So to get a power, the extent in situations in which we impose that there was no effect of the law, that could give us a sense of type 1 error. So the number of times we incorrectly identified an effect given there was no effect. And whether we recovered the effect magnitude appropriately. So we considered that was 3 states had the law. We considered 3 different law prevalence conditions. Again, drawing on what seemed to be occurring in the literature. So only a few states had the law. 3 states, 15 states, so some states, and then 35 states, like a decent chunk of states had passed this law at some point over the 1979 to 2014 period we considered. And then 3 law effect conditions. So the null effect, so we assumed the policy had 0 effect. So we just didn't adjust the data. We were basically just randomly putting fake laws in the data and seeing what came out. A negative effect, where we assumed that the policy reduced firearm deaths by about 3%. And that was chosen to get us to a situation in which, if in theory all states in the nation implemented that effect, we would reduce firearm deaths by about 1,000 per year. And then that, but just reverse, where we assumed the exact same thing, except instead of reducing deaths, the policy increased deaths. And then we had 2 kind of effect conditions to consider the course of the policy's effect, or the timing. We had an instant phase-in, so that would be similar to the dummy model, and then a 5-year phase-in, so where it gradually increased up to 5 years, and then the full effect of the law was felt from that 5-year point onward. So I kind of went through these before, but these are the different considerations we considered. So we focused on kind of a linear model, a log linear model, which I'll say is just a linear model where the outcome has been logged. So you take the log of the firearm death rate. 2 count models, Poisson or negative binomial, weighted by state population, the inclusion of the lags, and some of these other things that I got out before. I think the only thing here that may be of note is this type of coding. So we considered this effect versus change coding, which actually has not been considered in the literature, particularly because we were interested in how these autoregressive models performed. And so what I mean by this is when you're in a situation where you have an autoregressive model. So you're looking at the effect of some law on deaths, but you are including as one of your predictor variables the lagged value of those deaths. The very few studies in the literature that have kind of specified a similar model have tended to use effect coding. So it's just that dummy variable on the law. It goes from 0 to 1. The problem is when you do this in an autoregressive model, you have to remember that the effect of the law gets pass through, and then that outcome becomes a predictor. So you've, in effect, controlled partially for the law in your kind of like second stage, right? Because the lagged outcome goes in and it's picked up some of the effect of the law. By continuing to treat the law exactly the same, you've partially controlled it for its effect, so you're likely to underestimate the magnitude of the effect. And so I think this, I don't know what literature this is common is, but not this literature, but it is, in other literature, what people do is change coding. So instead of having the effect of the law go on forever, you just have a 1 for when the law goes into effect. So it's basically based on, it's like a first differences model. So it's based on the change from the year prior. So here you can see the change coding that the value of the law gets a 1 in the year it's implemented, and then it's 0 afterwards, because the effect of the law has now already been passed on through the next outcome and is going to be passed on in that beta B1 parameter there. This matters particularly when autocorrelation is high. So if B1 here is 0 and there's no autocorrelation, this doesn't matter. This would just revert to kind of the standard dummy model. But in the case of gun deaths, we have autocorrelation around 0.9. So really last year's firearm deaths really strongly predicts this year's firearm deaths with just some reversion to the national mean. And so in this case, this can have large effects. So we wanted to explore both of these options. And so that's one of the nuances to what we did that hadn't yet been, we hadn't seen in the literature yet. For all of our models, so there are 36 time varying state covariates we considered. I'm not going to go through them all. These are kind of commonly looked at in the literature in some way, shape, or form. I guess the only ones kind of worth particularly focusing on are these firearm-related measures. Often people proxy for gun ownership using the proportion of firearm deaths that are a suicide. So we considered that, but lagged 1 year. We considered the rate of non-firearm suicides and the percent receiving a hunting license, again, because they have been used as proxies for gun ownership. Whether you should include those or not is kind of still open for debate. Again, if you think part of the reason these laws have an effect is through gun ownership, you may say, well, then I'm not going to control for it. I can tell you for the most part, the model that I will say is the best model for right now is not sensitive to anything involving covariates for reasons that may become clear. Okay, so we've talked about this. Oh, I will say, again, because of this concern with overfitting, we did a principal components analysis to reduce those 36 covariates into 17 components. Those 17 components explain 95% of the variance in the covariates. And then we included year fixed effects in all models. Okay, and so how did we compare the models? So we had kind of 4 performance metrics, 2 which I've talked about, type 1 error rates. So the kind of probability that you'll find a true effect when it's not there, statistical power, the probability you'll find an effect when it is there. And then we considered kind of 2 more that I haven't seen as much in the statistical modeling or the simulation modeling literature, but I think are important particularly for this literature. So directional bias, which is, does the model tend to consistently over or underestimate the effect? So is it consistently kind of pushed up or consistently pushed down? And then magnitude bias. In terms of absolute value, are you tending to find far too large or far too small an effect? So this goes on for pages and pages, but I'm not going to show you all of that. So, oh my gosh, all of the models were horrible on type 1 error. Like horrible. So if you have kind of standard hypothesis testing, in econ it's p equals 0.1. In all other fields, I think it's p equals 0.05. You would want, so if that's what you're setting your significance value at, you would want your type 1 error to be around there, right? So if you're saying it's significant at the 5% level, that means you want like around 5% of the time you anticipate that a null effect would be found as statistically significant. In the standard 2A linear fixed effects kind of difference in difference model weighted by population, which is one of the more common in this literature, if you don't do any adjustments to your standard errors, you just do classic standard errors, your type 1 error is about 0.6, so 12 times as high as you want it to be. So you're almost always going to find a significant effect. Huber-White or robust adjusted standard errors don't perform much better. Clustering does the best, which is good. In this case, though, you're still kind of rejecting 4 times more than you would like to. I should note, so this is in the three states have the law prevalence condition. There has been kind of it's not even recent at this point. It was recent when I found out about it. There's been attention to the fact that particularly when you have few treated units, this clustering is not enough to get you appropriate inference. And when you have the 35 states implementing the law in the simulation, that cluster is actually quite close to 0.05. So if you have a lot of states that have the law, a cluster adjustment is probably sufficient to get you appropriate inference. But there are a lot of studies that are assuming that that clustering adjustment is fine even when you have few treated states, and that does not appear to be the case. So here, using the best standard error adjustment, so what performed the best for all of the 25 models, only 8 had type 1 error rates below 0.1. So this is averaged across all the law prevalence conditions and a lot there. And really, what had the lowest type 1 error, which may be a little too low, is the negative binomial autoregressive change coded with no state fixed effects. State fixed effects actually made this model perform worse. All models had low, so this is the power issue. So again here, all of our models, even this is highlighted because it's our preferred model. So even this preferred negative binomial autoregressive model where we don't have state fixed effects, but we have this change coding, even there, I think our highest power was 0.21, and that was the only model that had power above 0.2. So just anything you're doing in this scenario, you're just in a situation where you have low power. The effects of these laws and the variation in your outcome are just going to lead you to a situation where power is quite low, which may mean a frequentist approach is not what you want to do, but it's all I know how to do. So here, most models luckily only had small directional bias. Except for this linear two-way fixed effect model with a log transformed outcome, and that's because that's just increasing the skew in this case. So I don't know if it's taught that you should log transform the gun violence rate or something. I don't know why it's done. Almost all the papers that use this log transform outcome. So in economics, we just run it all the ways. So it's just reviewer 3 said run it this way. So you have 18 tables. That might be true in other fields. I'm not sure. But in others, they'll do this transformation to say this will improve kind of the distribution, but not show anything about whether that improved the distribution, and it could make it worse. And so in our situation with gun deaths as the outcome, it did seem to make things worse. And this was more problematic when almost everything is more problematic when you have few states that are implementing this policy. And magnitude bias was only a problem really for the autoregressive model with that effect coding, which is kind of what I talked about before, where typically those will underestimate the effects of the policy because you're kind of implicitly controlling for the policy by including that lag term. They underestimated it quite a bit, so by about 75%. And the model that I've already previewed this, that performed best on power, had good type 1 error, low magnitude bias, which was mostly from that few state condition, was this negative binomial was this model that nobody is using. So just to conclude, really some of the most commonly used models in this field are not well suited for evaluating the effects of state policies on the firearm deaths. Again, I can't speak to some of the other outcomes here because we only looked at firearm deaths. I will say we did look at kind of firearm suicides and firearm homicides, and this problem seems to apply there as well. And so I do think there's kind of some recommendations for researchers where not adjusting your standard errors or using only robust standard errors are problematic. You do need to somehow account for the serial correlation that occurs in this kind of time series data. Change coding, particularly in an autoregressive model, works far better than effect coding. And then really there are problems when only a few states have implemented the law in using these kind of standard regression models. There are other techniques that kind of are better suited. And then again, statistical power is low. So like I said, this kind of standard hypothesis testing framework may not be particularly useful in producing kind of the best possible estimate. And you may want to focus more on kind of credibility of whether the law has just an increased effect or a decreased effect rather than focusing so much on the magnitudes in this kind of frequentist framework. Thank you. I have 15 minutes for questions.
Hi, Rosanna. Thank you. That was a great summary. I was wondering, why did you guys choose 3% for your simulations? And is that a 3% absolute decrease across everything or 3% like relative within the rate by state? So
we chose 3%, so it's going to kind of depend on the model. 3% was chosen. So basically, in a survey of experts that was done as part of this project, we asked people kind of what they thought. Again, people on both sides, people who were both kind of thought we should have laxer gun policies and people who thought gun policies should be stricter, about kind of what the effect of a policy would have to be to really push for legislative change. And 3% was something everyone kind of agreed on. And by 3%, I mean that translates into 1,000 fewer firearm deaths per year. Right? So it's that level that we were going for. And in all of the specifications, whether it was the log link or the linear link, we tried to get to that 1,000 fewer deaths per year if implemented nationally, which is approximately 3%, but you should think of it more as if this policy were to be rolled out in every single state, we would expect either 1,000 fewer or 1,000 more firearm deaths per year.
Got it. Thanks.
So I guess I got a couple of things. So with respect to the log transform that they make, so for the Poisson and negative binomial, it's inherently a log link. But for the when you're using something like least squares or ordinary least squares, the underlying assumption is that the stochasticity in the data is normal.
Yep.
And so when you did this, did you look at what for the, well, actually, it's because you were doing a review of studies, and I know that most reviews, most of these studies don't do this, where they actually will plot what a QQ plot that actually tests to see if this assumption of the stochastics in the data is actually met by the actual residuals in the data. And you can do that not only when you're using least squares, but you can also do it when you're using like negative binomial or Poisson. And it's rarely done, actually, from what I've seen in the literature, and unfortunately should be more often done. You were talking about inconclusive and limited, like when you were talking about where you had that chart.
I'll go back.
Yeah, there we go. And so for the inconclusive, like when you were, so I've know mostly about the mass shootings literature. When you were talking about inconclusive, are you including studies that are rather questionable in their analyses? Is probably the best way I can put it.
Yes.
Yes.
So I mean, so inconclusive is it's no studies, inconclusive. Like that's our kind of lowest rating. And if you had at least one study, you weren't going to be in no studies. So you were already at the inconclusive bar just by having a study where, again, our only criteria for counting as a study was that pre-post and the comparison group. And so trying to get it like a causal mechanism. I will say for this there are more studies now for mass shootings for our update. But I think in this one, almost all of these mass shootings column are from one study. There's a study by Luca et al. That was published in 2016 that was actually about the effects of mass shootings on policy, but had an appendix table where they looked at the effects of policy on mass shootings. Completely an appendix. It's a linear probability model for the incidence of a mass shooting, which is highly questionable in terms of whether that's appropriate. So that was rated as kind of lower methodological quality, and which led to the inconclusive rating in all of those mass shootings. Some of the other inconclusives could have more studies that either were of similar methodological quality and came to diametrically opposed conclusions, or it could have been a number of studies that we all viewed as having kind of more severe methodological problems.
All right, thanks.
So one of the things that struck me is when you have these hugely inflated type 1 error rates, that tells me that those models are badly misspecified models to the real data. And I would wonder if you did any other looking at the data to try and figure out in what way it was misspecified, so you could try to figure out what would be more close to the correct model. Because one thing that I've never seen, I've looked at some of these policy papers, I've never seen people do it, but I was thinking, well, what if you just fit like a generalized additive model to the pre-policy era and then one to the post-policy era, and then combined them into one model and compared them with like a likelihood ratio test or something. And I would wonder if the misspecification is in the mean structure, that kind of trick could work.
Yeah.
but it could be something else. And I was wondering if you actually looked at anything like that.
I don't think we looked at it that closely, and I also haven't seen that done, though I think you're right that that would give you some insights. I do think kind of in going through that simulation, even though you can do some adjustments to the standard errors that get you close to the right type 1 error rate, I think we still prefer the autoregressive model that doesn't require those adjustments, because we do think that indicates that it's more appropriately specified for the outcome of interest. So all those standard error adjustments that you can do, and I mean, you can do, falsification. You can get the right standard errors, but maybe it's more important to correctly specify the model. I think that point's well taken.
I'll start this way.
So you didn't say Bayes anywhere. So I'm assuming that this literature really has not taken a Bayesian approach to these issues. Is that correct?
For the most part, it has not. I did take out, so with Terry Schell, Andrew Morale, Matt Cephalou, and Beth Ann Griffin, we are working on applying what we learned about the model that we think is most appropriate with Bayesian methods to try to estimate the effects of concealed carry laws, child access prevention laws, and stand your ground laws. And I'm not going to pretend that I'm an expert in Bayesian methods, but I can preview, and it says don't quote us on them, because we're still working on it, but we really did try to, that's exactly the direction we wanted to go, because we do think it's more appropriate. So basically, we took the model that was identified as optimal, that autoregressive with the changed coding. There's some details on, we allowed for a kind of a flexible structure in how the law rolls out, so how that kind of law's effect is felt over the 6 years. And yeah, so that was based on additional simulation analyses that I don't remember. But anyway, so then we focused on these laws, again, because enough states have passed these that we thought we didn't have that problem with the few treated states. And this was implemented as fully Bayesian with some priors that assume the mean law effect is 0% and a 7% standard deviation of the effect. That was based on the expert survey. Again, I didn't get into this because not an expert in Bayesian, so if there were going to be experts in Bayes here, I was like, I won't know what to tell you, but I can show you the preliminary results, which here, so again, we're kind of plotting out all of these, and so these are going to be kind of the 95% credibility intervals on the right here. This is for child access prevention, where basically, like, this was actually one with the stronger evidence where, I can't remember the probabilities off my top of my head, but we're fairly certain those are decreases and not increases in total homicides, same with suicides and deaths. If you want to focus specifically on firearm homicides and firearm suicides, that's what we're finding. For stand your ground, here, and this black line is kind of plotting out the average of the time course. I think it's, that's the median, median of the time course. And so for here, we're not finding much on suicides. We're finding, if anything, it appears to be an increase in total homicides. Any of the effects on total are going to be driven by firearm. I can just preview here. So that's just laying on firearm homicides and firearm suicides. The right is always going to be total deaths. And then this is what I guess would be closest to the concealed carry. Here, again, we're specifying, and people have done this differently, but we're specifying particularly this is moving from may issue to shall issue, which is far more common. I think there's far too few that went straight from no issue to shall issue to be able to implement that. And I think the takeaway from even before doing this was, given the low power, it is unlikely that these laws have gigantic effects, right? Like, we would have found it by now using a frequentist approach, and I think these kind of bear it out, where we can tell you pretty much about the directionality. These are going to be small effects, so this is going to be the IRR on the left-hand side, but they do tell us something about what we think about directionality.
Great, and the new set, you mentioned about another set of 30 or so studies.
Yes.
So that sets you up perfectly to take a sort of Bayesian approach in terms of updating the model structure.
Yeah.
And I might consider that.
I will. Thank you. That's a great idea.
I think that was a wonderful review of these models. But following up on the earlier question, one way I can imagine that these models are all misspecified and the one that's most obvious to me, is that this is not a problem. This is many, many
Yeah.
different problems that we're combining all the data into one thing. And there's no reason to believe that there's one model that's going to fit them all. Is there any way to get enough data to represent context as well as just outcomes?
Well, Sherry's the one who hoards data. So if anyone has it. I don't know. I think that's a good point. And I will say, even these simulations are kind of, we're artificially imposing an effect. We're simplifying the problem even. And this is far more complex than that. It's far more complex in a number of ways. Like, it's not just one policy. States have kind of a bunch of policies that are enacted. And to be able to say something about kind of the basket of policies that any state has in effect, I think it may require something outside of the empirical data, and maybe somewhere where this kind of mathematical modeling actually has a lot more to say than we can say with statistical models.
Is there anything on, oh.
So I love the presentation, and I'm reminded a little bit of a presentation that Daniel Nagin gave a few years ago after the National Academy of Sciences did another review of death penalty research and the empirical basis for estimating the deterrent effect of the death penalty. And at the end of that, they came to, and I'm butchering this slightly, they came to the conclusion, we cannot conclude anything on the basis of the empirical literature. So where are we with respect to, that was very strong non-claim on the National Academy of Sciences part for that sort of crime literature. How close or far are we from this? Because he was criticized at the time. People said, gee, Daniel, like, so then we should make our decision on whether we are a fan or an opponent of these policies entirely on the non-empirical domain.
Right.
Whatever our commitments are, whatever other considerations we have, you've just eliminated the empirical literature from contributing to the discourse on this.
Yeah,
Perhaps
it's not uncommon.
Perhaps a brutally honest thing. But how should we think about that with respect to results that are so sensitive to model specification, at least to date?
I mean, I think my response would be, particularly in areas where there has been a lot of work and these results appear to be highly sensitive, it is unlikely that the effects of this law are very large, right? I think it's still important to know whether it's harmful or beneficial, but maybe they're unlikely to be huge in magnitude. Otherwise, you would face less of this sensitivity. I think I'm not a policymaker, but from a policymaker perspective, they often have to make decisions without all of the evidence being in. And I do think, so I think we have some policies and some outcomes, which is, I guess, the point of that slide. There are some where we have stronger evidence. And so maybe those are low-hanging fruit, and maybe those are policies that can be enacted. There may be some, unfortunately, I think particularly in this space, there may be some policy outcome pairs where regardless of how supportive the empirical evidence is, you're not going to change people's minds. People will have their priors, or they're not making their decisions based on the empirical evidence. And from my perspective as a researcher, all I can do is try to provide more empirical evidence or try to kind of highlight where there is or is not. I leave it to the policymakers to figure out what to do with that.
All right. I think let's thank Rosanna.